We are starting our unit on kinematics, which is the study of motion and how things move. So I want to start with a question. How can you tell that something is moving? Are you moving right now? How do you know if you are or not? Maybe you're sitting in your desk looking at your computer, real quiet, real still. Are you moving? Well, maybe the veins in your heart are, or maybe if you take our little magic school bus of science and zoom way out, you can see us zooming by as the world turns. Whether or not you're moving depends on your frame of reference. Is your frame of reference the blood that's coursing through your veins? Is it the International Space Station or the Earth or the sun? Your frame of reference will tell a lot about how you're moving relative to that position. So a frame of reference is anything that we can use to compare motion. Most commonly we'll use something either part of the earth or attached to the earth, like a telephone pole, those electric line poles. Maybe if you're driving, you could use mailboxes to tell how far you've gone, mile markers. If you're on a football field, you use the yard line markers. Any of those are stationary relative to the rest of the things that are buzzing around. So those are the things that we're going to be using as our frame of reference. Now, we talked a little bit about this when we talked about vectors. How far your object moves total is its distance. But then at the end of the trip, when you compare where it is now to where it began, that origin, then we get something called the displacement. That's how far it ends up from where it started, according to that frame of reference. So we used something like this. We talked about if I walk 2 miles to the store and then I turn around and walk back, what's my distance? Well, I've walked 2 and then I walked 2 more. So my little pedometer thing is going to give me credit for 4 miles. But what is my displacement? How far am I from where I started? I'm right back where I started. I'm at 0, so I have a displacement of 0. So displacement is just how far you are from where you started. In this case, I'm right back where I started. Distance is the entire trip. So these vectors that we talked about, they can show the magnitude and the direction. Now, magnitude is just a fancy word for amount. They can show the amount of travel that we have, and they can show us the direction, how far we went. Now, the opposite or the other side, the other type of measurements from vectors are what we call scalar measurements. They only show you an amount. So the weight that you see on the scale, that's how I remember a scalar, is like a scale. The time, there's no like north, south, east, west with time. How old you are, those are all things that just give you a number. They don't have a direction associated with it. We talked a little bit about how to combine vectors. If they're in the same direction, then we add them together. If they're in opposite directions, then they kind of cancel each other out, like the example where we walk into the store and walking back. So we would subtract those. If they're at angles, then we need to use our trigonometry and our Pythagorean theorem, possibly even our sine, cosine, tangent, to figure out those angular measurements. Now, in addition to distance and displacement, there's some new motion words we're going to throw in here. Speed, velocity, and acceleration. And I'm sure you've heard these words before in your everyday language. Change happens. We are not going to stay in the same place the rest of our lives, of course. So how fast we can change our position, whether we're running out of this classroom or whether we're just walking calmly, gives us the rate at which we're changing our position. So speed is how fast we're changing where we are relative to that frame of reference. Okay, so we can calculate speed by taking our distance, how much position we've changed, and divide that by how long it took to do that. So we have cars that we drive in. Some of us have really fast cars. Some of us have kind of clunkers. All the cars can go from here to home. But some cars can do that a lot faster with less time than other cars. Okay, so speed is how fast you're changing where you are. We can look at 2 things. We can look at the average speed, which is the total distance that you covered divided by the total time. So for example, if it takes me 2 hours to get to Dallas, Dallas is 120-ish miles away. What's my average speed? Okay, distance, 120, divided by time, 2 hours, that'd be 60 miles per hour. But does that mean I've been going 60 miles per hour since I pulled out of my driveway? Absolutely not. You're going a little faster on the highway, you're going a little slower in town. So when we're looking at what's actually showing up on the speedometer, that's your instantaneous speed, how fast you're going at that moment in time. So for example, in Canton, I got into heavy traffic. I was only able to go 50. That 50 is how fast I was able to go at that time. That would be my instantaneous speed, okay? Velocity is sometimes used interchangeably with speed, but there's a key difference between the two. Velocity is a vector, okay? So velocity is going to show the speed, but it's also going to show which direction I went. So when we're including direction, we can include north, south, east, west. We could go west to Dallas. We can come east back home. But we can also make it positive or negative depending on the direction we're going. Forward could be a positive velocity. If we turn around and put it in reverse, that could be a negative velocity. We could be going backwards. Not that we're so slow we've negated ourselves, but that we're going in the other direction. We're not going in a positive direction anymore. We're going in a negative direction. So velocity is the distance, the change in position, divided by the time that it took to get there. Very similar to speed, but it can also include that direction to it. So for example, if we are going 25 miles per second, or meters per second, sorry, that's a speed. But if we're going 25 meters per second west, that's a velocity. 4 kilometers per hour, speed, negative 4 kilometers per hour, that means we're going back to our origin. That would be our velocity. We can graph our motion in a position time graph, and here's an example of that right there. You have distance, which is your dependent variable, because where I am depends on how long I've been traveling. So time is independent, that's along the bottom. And you can see from 0 to 6 seconds, I was going away. I was making a positive change in my position. From 6 to 11 seconds, I was stationary. So there was no change in distance. I was at 10. Come back and check, yep, still at 10, come back and check, still at 10. Then if you look from 11 seconds on, I have returned back to the origin. So returning back to the origin puts me going in a negative direction. I'm going backwards, so that would be a negative velocity, okay? Now, velocity is calculated as our change in distance divided by our change in time. In this case, it's our rise over our run. Aha, you get a connection here? Slope of our graph is velocity. So if we were to calculate the slope between 0 and 6 seconds, we could find how fast we're changing our position, which is our velocity. So you see positive slope, positive velocity, negative slope, negative velocity. So here's an example position time graph. We find that rise, that how much we've changed our position. We find that run, how much we've changed our time, how much time has gone by. Our slope is our velocity, okay? In the case of the box on the bottom right of your screen, you notice how that line is curved. That's a changing velocity. We're accelerating. We're going a different velocity as time goes on. So in that case, if you look for your instantaneous velocity, it's going to be that tangent line. Do y'all remember tangent lines from math class? So that line tangent to your curve will give you your instantaneous velocity. If you were to take the beginning and the end points, you could find your average velocity, but that doesn't mean that you've been going that the entire time. So when we change our velocity, that's a term called acceleration. We don't go the same speed our entire lives. Like the example of driving to Dallas, in my neighborhood, I'm going slower, but then I speed up for the highway. So acceleration is how fast we change how fast we're going. It can be positive or negative as well because it too is a vector. Since velocity is a vector, acceleration is going to be a vector. Okay, so we could have positive 2 meters per second squared, and we have per second squared because it's meters per second. Okay, so we combine. We could have negative 2 meters per second squared, which would mean that we are either decreasing our velocity or we could be going backwards. Either way could be happening. So beware that acceleration is our change in velocity. Acceleration, or velocity rather, is how fast we're going, but it's also the direction. So, and velocity, including both speed and direction, we could be changing our speed, but we could also be changing our direction. So if you see down here the little b that's going in circles, the little b is constantly changing its direction, so it's having to constantly accelerate. And that will come in handy when we talk about circular motion. Circular motion is a constant acceleration, not because it's changing speed, but because it's changing its direction. So we can graph velocity just like we graphed position. They look very similar, but we're going to make ourselves a way to organize the way that they look and interpret these graphs because they can get pretty confusing. They look very similar. So if you notice on our graph down here, from 0 to 10 seconds, we have gone from 0 meters per second, we were not moving, up to 15 meters per second. We sped up. We have a positive acceleration, okay? From 10 to 20, the line is flat. Now, it doesn't mean we're not moving. In the previous graph, it meant we weren't changing our position, but here we're not changing our velocity. When we're not changing our velocity, it means that we are on cruise control. We're going the same speed, but we are moving, okay? Between 20 and 30, again, we're speeding up. And then notice from 30 to 50, our velocity is decreasing. We're not going backwards. We're still going forwards. We're still making positive gain in our position, but we're doing it at a decreased rate. We're doing it slower than we were before. So that's a negative acceleration, meaning that we're slowing down, okay? We can find acceleration from velocity time graphs, just like we find velocity from position time graphs. We're looking for that slope. So here's another one. We've got acceleration in the blue line. We've got a steady speed, not stopped, just going the same speed on the red line. And then you see the green down there is deceleration. It's slowing down. Okay, so that is a quick intro to distance displacement, speed and velocity, and acceleration, okay? We're gonna take this, we're gonna use it, but make sure that you have those terms down and you know what they all mean and you know how to calculate those.